Our topic today is multiplication with the area model. So we're going to start off talking about numbers, and you probably don't remember, but back in the third or fourth grade when you talk about multiplication, one of the ways that they stood to get you to understand the idea of multiplication is using what's called the area model. If I envision a rectangle, one side is 5 and the other side is 6, you guys know the area is 30. But the reason the area is 30 is that I have rows. There are 6 items in this row, and there are 5 rows this way. So 6 and 6 and 6 and 6 and 6 adds up to 30. The reason that multiplication works is because of you visualizing it in this manner. Okay? So that's the basics of multiplication with the area model. It looks a little bit different now if we break it apart. Let's say instead of calling this 6, I called it 2 plus 4. Well, it's still 6. I've just broken it into 2 and 4. And this side, instead of calling it 5, I've called it 3 plus 2, which you know is still 5. So I now can think of each of these as having little rectangles. So this little rectangle here is 3 by 2, and 3 times 2 is 6. This one would be 3 times 4, or 12. This one would be 2 this way and 2 this way, so it would be 4. And this one would be 2 by 4, or 8. If I add up 6 plus 4 plus 12 plus 8, I get 30. Okay? So I haven't changed the area, I'm just thinking about it in pieces. So we're going to talk about what that looks like in this class when you start multiplying. Okay? We all remember the distributive property, we use that a lot. Using the area model, if I had a problem that said 6 times the sum of x plus 4, I could think of that as 6 over here and x plus 4 on the top. I have to break it up because I don't know what x is, so I can't think of that as a number as one together. So I do 6 times x, so this one would be 6x, and 6 times 4, 24, and I get 6x plus 24. Now, you probably don't need to create an area model for this. You would just go 6 times x and 6 times 4. But I want you to think about what's going on. When things get a little bit more complicated, you might want to build yourself an area model to solve some problems. Let's look at some 2 binomials being multiplied. Now, we often would use something called FOIL. I'm not sure what your teacher taught you, but some students will have used FOIL in Algebra 1 to multiply this together. That stands for first, then outer, then inner, then last. And we multiply all of those pieces together, combine them, and we get the answer. But if we put it into the area model, we'd get something like this. Here's my x minus 1. Here's my x plus 3. It doesn't matter which one of these goes here and which one goes here. I'm going to get the same answer. So now I say, well, the first thing I would do is multiply x times x and get x squared. Then I might say x times 3 and get 3x. Come over here and I have an x to negative 1, I get negative x. And I have a 3 to a negative 1, so I get negative 3. Now, the like terms, it turns out, are always on the diagonal. See how I have x and x here? So I said x squared plus 3x minus 3, and then I combined 3x minus x to get 2x. So my final answer would be x squared plus 2x minus 3. Again, you might be very comfortable with this and be able to just go boom, 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 and have that answer quickly. No reason for you to create an area model. That's perfectly fine. So let's talk about a couple of more complicated polynomials. Now I have x to the third minus 5x squared plus 2x plus 1. And then the other number is negative 6x squared plus 5x minus 2. I need to multiply these two together. Now it might get a little bit more complicated. Maybe the area model will help me keep track of what I'm doing. So I place it in here and I decided to put the x to the third, then minus 5x, then 2x, now 1. Important thing to note is if I have a negative in front of my coefficient, I better bring that negative down into the model or I'm going to get a wrong answer, because it's going to be important in my multiplication to keep track of the negatives. This is not a 5, this is negative 5. Okay, so here it goes. So I said, well, let me multiply I put this negative 6x squared, then the 5x, then the negative 2. Okay, I multiply it in my first box, negative 6x squared times x to the third, and I get negative 6x to the fifth. If you don't remember how to multiply exponents and what you do, you need to go back to another video or back to some other remedial notes and remind yourself how you do that. Okay? So I multiply these two terms and I get this. Multiply these two terms and get this, -6, -5, +30, right? Multiply these two terms and get this, and so on. And I do that. Now I'm going to multiply this times this times this, and I find each of their intersection points in that square. Okay? And I go all the way through it, I get a huge mash of numbers. The important thing now is, as I combine like terms, I notice I only have 1 to the 5th term, so here it comes. But I notice I have 2 to the 4th term, so I'm going to add those two together. 30 of them plus 5 of them, and I get 35. Okay? Then now I have 3 that are x to the 3rd terms. This is just coincidental. It's more how many do I have on the diagonal than driven by anything else. So I have -25 and -12, which is what? -37. 2 more negative, -39, and that comes here. Now I have x squareds, I have 3 of them, 10 and 20, -6, 14. Now I have 2 x's, a 5 and a -4, 5 minus 4 is 1, and then one little integer here by itself, -2. This is the solution to that problem. So now I hope you could see where a complicated expression would benefit from putting it in the area model much more so than one of the simple ones would. So now I would like you to use an area model just to practice it, even if you're just amazing at this, and try this problem. So put this on pause for a second and set up your area model and solve this. While I look for a marker to solve it myself. Seriously. Wow, that was awkward, wasn't it? Okay, so here I go. I'm going to decide to put 4x to the 3rd, 2x, -5. Make my somewhat of a rectangle. And then I put my x squared and I put my +6. Okay? So let me break it apart and start my multiplication. X squared times 4x to the 3rd is 4x to the 5th. X squared times 2x is 2x to the 3rd. And x squared times -5 is -5x squared. Now I get to multiply all of these by 6. 6 times 4, 24x to the 3rd. 6 times 2, 12x. 6 times -5, -30. Okay? So let's pay attention here because I have slightly different, because I'm missing a term here on the x's, my numbers aren't going to be perfect on the diagonal. But I do know I only have 1x to the 5th. So here we go. 4x to the 5th. I have 2x to the 3rd, so let me add them together, and I get 26x to the 3rd. This is an x, and this is an x squared, so I'm going to do the x squared next. -5x squared, and then the x, plus 12x, and last, -30. Because I always want to write those polynomials in largest to smallest exponent. Okay? Fifths, thirds, squareds, x, 30. I didn't have any fourths, so that's not an issue. Okay? Hopefully you got that same answer. If you didn't, I would suggest you go back, follow through both of these two problems again until you understand how it's done. Now, question I often hear from students, do you have to use the area model? No, of course not. This is another tool available to you. If you are just fine using the normal distributive property, you know, the whoop whoop like we would often do, this is how that would look. Okay? I take the 5x squared and I multiply it by each one of these things, and here's that. Then I take the -2x and I multiply it times each term, and there's this. Notice I'm lining up my like terms as I go, because then I find it'll be easier for me to combine them. Then I take the 3 and multiply it times all 3 terms and get this. And then I add straight down. 30x to the 4th, 10 and 12 is -22x to the 3rd, 25 and 4 is -29, but +18, -11x squared, 10 and -6, 4x, and 15, -15. So this would be my final answer on this problem. Okay? So you don't have to use the area model. I want you to know how to use it. When you get complicated problems, it might help you out. If it's not helpful to you, then that's okay too.